Up to this point, we were exclusively discussing power series centered at 0 when talking about Taylor series. This, of course, doesn't have to be the case. To illustrate this, let us consider the following example. Let us take a simple function, say sine x, and find its Taylor series. At, say, a point a equal to pi over 3. Then let us also find the radius of convergence. So recall what Taylor series of a function is. It's the following sum where we have the kth order derivative evaluated at point a divided by k factorial times x minus a to the k. In other words, to write down this expression, we will need to know the kth derivative at the point a for any k. Fortunately, derivatives of sine are periodic. They repeat with the order of the derivative, so this will not be very difficult to compute. Right, so the zeroth derivative of f, as usual, is the f itself, in this case sine x. The first derivative is cosine x. The second is minus sine x. Third is minus cosine x. And finally, the fourth derivative is again sine x. So there we have this periodicity of derivatives revealed. Let us go ahead and evaluate derivatives at the point a. So in our case, of course, a is pi over 3. So first, the value of our function at pi over 3 is sine of pi over 3, so that would be root 3 over 2. The first derivative at pi over 3 is cosine at pi over 3, so that is 1/2. The second derivative gives us minus sine at pi over 3, so that would be minus root 3 over 2. The third derivative gives minus cosine, so that evaluated at pi over 3 gives minus 1/2. And finally, the fourth derivative is again root 3 over 2. Great. So here we have all the distinct derivatives listed. Let us see what the series for f of x will look like. So we will start off like this. First we will have the value of f at pi over 3, then the derivative at pi over 3 divided by 1 factorial times x minus a, in this case pi over 3, plus the second derivative at pi over 3 divided by 2 factorial and multiplied with x minus pi over 3 squared, and so on. Let's write maybe another term. Actually, should probably suffice. Let's see. No, yeah, we do need another term to make the dependence on k clear. Let's write the third derivative, pi over 3. We won't need to write the fourth derivative though, because that repeats the 0th order derivative. Here I have 3 factorial and x minus pi over 3 cubed. Great. Now let us substitute all the relevant quantities. So we have f at pi over 3 equal root 3 over 2. Then I have to add 1/2 the derivative at pi over 3 divided by 1 factorial multiplied with x minus pi over 3. Okay, and then the second derivative is negative. So I will be subtracting root 3 over 2 divided by 3 factorial and multiplied by, this would be 2 factorial. 2 factorial and multiplied by x minus pi over 3 squared. And finally, the third order term, I have the third derivative should have been minus, like so. The third derivative, minus 1/2 divided by 3 factorial multiplied by x minus pi over 3 cubed, and so on. So the pattern that reveals itself is that the even order terms are multiplied by root 3 over 2 and their signs alternate. The odd order derivatives, so this would be the 0th and the second derivative, and the odd order ones, the first and the third, are multiplied by 1/2. Their signs also alternate. And so if we are to summarize this in a single expression, we can write this as the sign x as a sum of 2 series. So first, let us write down the even order terms, the 0th, second, fourth, and so on. So here we have the sum k from 0 to infinity. As I mentioned, the signs must alternate and they start with a plus, so we have -1 to the k. And then the even terms are multiplied by root 3 over 2. So here's root 3 over 2. Then I have the factorial of the corresponding index in denominator. I have 2k factorial in the denominator, and then everything is multiplied by x minus pi over 3 to the 2k. So if you consider this expression, it covers the odd order terms, where you have root 3 over 2 divided by the corresponding factorial multiplied by x minus pi over 3 to the 2k. And as to the odd order derivatives, the terms that contain odd number derivatives, for them we also have alternating signs starting with 0. They have to be multiplied by 1/2. So we'll just put 2 over here. Then I have the corresponding factorial, which in this case is 2k plus 1. So you can see that we start with 1 factorial, and so that corresponds to the k being 0. We have 2 0 plus 1. So indeed, the very first factorial is 1 factorial, and then we increment the argument that is passed to the factorial by 2 every time the index increases. And finally, we multiply everything by x minus, I may have to put it in the numerator here. We have to multiply everything by x minus pi over 3 to the same degree as is the expression under the factorial. So this would be 2k plus 1 in this case. And so this completes the Taylor expansion for sine x at pi over 3. We have to represent the expansion as 2 different sums because the corresponding expressions are slightly different for the even and odd numbered derivatives. Here are the different factors here. And so in fact, the radius of convergence, the second question from this example, the radius of convergence for this series is infinite. And this is shown just as for the Maclaurin series of sine x. So I will skip this computation and leave it to you as an exercise. Show that this series here is convergent for all x's. So of course, it suffices to apply the ratio test. And so this completes our example of computing a Taylor series for a simple function, in this case sine x. So of course, in general, if you have more complicated function and less pleasant center for your series, this computation can become much more cumbersome, but all the essential elements are already there. So this is the computation that you always go through. First you tabulate the derivatives, then you write down the infinite series just as we did over here. So all of these elements are always employed when computing a Taylor series, regardless of which function you're dealing with.